All right, welcome back for part two of the transformations video. Um, we're asked in example two to graph this function, and there's a bunch of transformations there. We'll worry about what's going on in this thought cloud after. We'll talk about that. But first of all, I think the key is identifying not only the transformations, but what's the parent function here? If I sift through all this junk, what's the basic graph, the basic card from last day? Well, it's the exponential function 2 to the exponent x. And these parent functions we have to be able to graph very quickly without much thought. And then we have to be able to transform them. So what are the transformations to the parent function? The minus 3 isn't in with the x, so this is a vertical something. Vertical what? Well, the minus, it's a vertical reflection or a flip. Vertical reflection, so it means that where the graph was going like that, the basic graph, now it's going to be flipped and going down this way. So it's a reflection, but it'll also have a 3 multiplied by 3 there. So what does that do? That expands it by a factor of 3. In the direction of y, it's what you would think. Of course, in the direction of x, it's opposite. We think plus 2 would move it right, but it actually moves it left 2. And this 4 isn't in with the x, so it's not affecting x values. It's not moving it horizontally, it's moving it vertically. So this is down 4. And what we're going to do is we're going to do the basic graph, and then we're going to do our reflections, compressions, and expansions first. Usually expansions first, then what we call the translations, the moves up, down, left, or right. As we'll see, not always. This is something that you're going to investigate with homework tonight, is this idea, do I always do the reflections, compressions, and expansions first? All right, well, let's get into the graph. Get some scale going here. I'm going to draw a bit of a weird scale just because the nature of our transformations kind of mess up with this graph. So I'm going to have each 2 ticks is worth 1 in the direction of x, and in this way each tick is worth 1. So you see my scale? And you don't have to do the same scale as me, but if you do, then our graphs will look the same. So I'm going to start by graphing the parent function. Sometimes we can skip the parent function just because we've had some practice at this. So the exponential graphs, remember, all of them go through 0, 1. And then the next point is 1 and then the base, and the base is 2 here, right? 1 and then the base is the next point. And then I think of a point on, oh, that's supposed to be minus 1. In the direction of over here, minus x is minus 1, gives you the flip of the base right there. So this is the point, negative 1, a half. Well, how is it a half? Well, remember, 2 to the exponent minus 1, x is minus 1. The negative exponent means for you to flip the base. Remember that from grade 11? And these 3 points I should be able to fit on any exponential graph. And remember that we graphed kind of that in grade 11, where a was any base, and the base would be a, and the base would, over here would be 1 over a. Now, since this is good old 2 to the exponent x, I can fit some other points in here. For instance, 2 to the exponent 2 is 4, and that gives me that nice point. And I might even be able to fit in, there's 4, 5, 6, 7, 8. 2 to the exponent 3 is 8, so I can actually fit in another nice point. And of course, I remember the shape that there's an asymptote. And trying that, it's kind of wobbly, but not bad. There's my basic graph, and I'm going to do then next, I'm going to do the 2 stretches and flip next in one step, if I can, because I kind of want to do that thing first. vertical reflection and expansion by a factor of 3. So I'm going to start on my y-intercept, and if I just flipped it, it would be here. But I'm going to flip and stretch. Where it was 1 unit, now it's going to be 3 units. And notice nothing's going on horizontally in these stretches, so I don't have to worry about where it's going horizontally yet. Just reflection and then stretch. So where this distance was 2, it's going to be -2, the reflection, and then stretch to 6, right? 2, 4, 6. A nice big point there. And notice this one would stretch or flip to, oh, hang on, let's do this one first. Flip to -4, but then stretch by a factor of 3. Where would it be? Off the graph, -12, right? That point would end up at -12. Flip to -4, multiplied by 3, -12. This one I can do. It was a half. It would flip to -1/2, but then expanded by factor of 3 to 1.5. And I can see my asymptote there stays the same. So about the thought cloud here, the stretch and reflection never changed the asymptote at all. But we'll see that the translations do. What's the graph of this red one? Well, all I've done is my flip and my stretch, my reflection and expansion, and so there's the graph. And now I'm going to do the transformations, translations rather, in one step. Okay, so what I'm doing is getting a copy. I want a copy of my asymptote. So if I can grab it, I'm going to make it a different color so you can see what I'm doing here. All right. Maybe make it dotted too. There, lovely. So what happens, we said when we flipped it, nothing happened to the asymptote, but when we move it, left 2, okay, left 2 won't switch it. So where it was here, left 2, okay, it's still on itself. But when I move it down 4, 1, 2, 3, 4, that's kind of like where the new asymptote is. And that's kind of an important deal, isn't it? This is going to be the line y equals -4. The asymptote has been moved down as well. Now I could think of either reproducing this red one again in relationship to this new asymptote, or I could move all of the points left 2 and down 4. Well, why don't I do that? That sounds easier. Left 2, down 4. 1, 2, 3, 4. Ah, and see, there's that relationship. I'm 1.5 units off the asymptote, just like I was here. Left 2, down 4. There's that 3 units off of the asymptote. Okay, lovely. And in fact, now when I move left 2 and down 4, I'm going to be off my graph. And so these 2 points are the only points that'll kind of fit on. Lovely. And now what are we going on about the thought clouds here? What effect do the transformations have on the domain and range? Well, the domain is still all real numbers, even though I can't see the graph covering up and having a shadow on the x-axis here. This is going to go on forever in this direction, and x can be any real number. So it had no effect on the domain. On the range, we can see the range of the black one was y is a member of the reals greater than 0. But now, what's the range? So we said the domain is x is a number of reals. So there's no change. The range, though, is y is less than, it's from a hole there and all these down, y is less than -4. Intervals of increase or decrease, where it was increasing on all numbers, on all real numbers x, now it's decreasing. The end behavior, well, the end behavior was as x goes to -infinity, y goes to 0, but here as x goes to -infinity, y goes to -4. And that's got to do with our asymptote change. Of course, when x goes to positive infinity, what's going on? Well, for the black graph, y went to positive infinity, but it doesn't now. And that's got to do with the idea of it decreasing now instead of increasing. And the transformation that accomplished that, of course, was the flip. The flip was the thing that changed it from being going to positive infinity to negative infinity. Write g at x as a transformation of f. So this idea is very similar to the 3-minute review, where we want to write g as a transformation of f. So the idea of we have f at x instead of our parent function, except for we got numbers all over the place in here. So we don't want to just write f at x like this because we've got transformations. Well, what transformations? Well, get a little more room here. Well, we said it was flipped and expanded. And in with the x in the function f was a move left 2 and also down 4. So notice the f kind of takes the place of the parent function 2 to the exponent x, and then I can write one function as a transformation of the other. Easy peasy. All right, we got one more example, and this has got more to do with the textbook's method of doing transformations, and we'll mention that. But I'm going to think about it in terms of a graph. Notice that we don't have any information about what this function f is. All we know is that 3 minus 2 is on. That's it. And we want to find the coordinates of the point on this new graph. This is kind of like the g of x. So that's on that. Where does this point end up on the new graph? Well, what do these transformations do? This moves it vertically expansion by a factor of 2. Vertical expansion, factor 2. The plus 1 in here is opposite that you think, since it's in the direction of x, moves it left 1. And so, you know, even though I don't have a graph, I could think of it in terms of the graph. So where does 3 minus 2 end up? Well, vertically expanded by a factor of 2 means the y coordinate, its vertical distance doubles, so it's minus 4. And moving left 2 means that gets subtracted by 1. There, done. Now, I want to mention the way the textbook would do this. The textbook would get a formula, right? They'd say on f, if we have the point x, y, what is it on this equation y? What does the transformations do? Well, left 1 means the x coordinate gets subtracted by 1 and the y coordinate gets doubled. So then they have this formula in general, and then you can just shove it in, the x and the y into these little formulas, and you get the same thing that we thought of by the graph. And this is the textbook's way of dealing with it. Rather than I think of the picture, the textbook uses a formula, and you're welcome to use either way. We'll see that it does get a little more complicated when the function gets more complicated, right? So here, let's think of all of these transformations. This is a vertical reflection and expansion by factor 6. The multiplied by 2, and notice the brackets here, multiplied by 2 is a horizontal. You think it would be a horizontal expansion, but in the direction of x, it's opposite, right? So you think it would be expanded by a factor of 2, but it's actually compressed by a factor of a half as far, right? It's kind of like dividing by 2 instead of multiplying by 2. The plus 2 here is a move left and down. So if we were graphing this, we know that -3 is a point on f, and this is kind of the rest all way. I'm not thinking about the book way. We'll go over the book way in a second. But I would do all of this stuff first. The expansions, compressions, the flips first. So What happens to the y-coordinate if we do these two first? I'm doing that one first. Well, horizontal compression means that the y-coordinate gets divided by 2. So that means it ends up at, what's it, -3 too? Oh, I goofed that up. So it's +3, -2. So that gets divided by 2, right? And I'm just doing the expansions and compressions and flips first. And what happens to the y-coordinate? Well, it gets multiplied by a factor of -6, flipped and expanded. So instead of -2, I'll have 12. And I'm thinking about the picture, right? And so then I'm going to take this point, and then I'm going to move it left and down. So then I think of the next point then, left and down. Left 2 means this goes from 1.5, left 2 would be to -0.5. And then down 3, well, it was at 12, we move down 3 to 9. And there's the point. That's the end point. Now I want to mention how the textbook would think of this. Again, they're going to think of the formula. And again, I'm going to do this in 2 steps. So what was the first step? Was a horizontal compression. So whatever the x was, they divided it in half. Whatever the y was, they multiplied by -6. And then the move left and down, and means this one becomes this point left. You take this and go left. You take this and go down. And there's the expression. And now if I want to get my transformation of that point, then I can fill it in my formula, and you get exactly what we got by thinking of what the graph would look like. And again, you can do it either way, textbook way or old school way. Quite a bit of homework here. And notice generally we do compressions and expansion first. There's a bunch of the homework, and then there's this handout. This handout we will, I believe it gets taken up at the beginning of the next video, I think. And I might be lying to you, but I certainly hope not. Good luck on your homework. The FAQ, there's an FAQ today just like every day. Transformations.